Welcome to yet another exciting episode of Fun with LC Tank Circuits. And what we're doing this go round is I thought I'd take a look at the different behavior of what's termed the electromagnetic near field and the electromagnetic far field. I'd heard about those things and I always knew that, they behave a little bit differently. But until I took the time to actually look at it, they behave way, way differently. And it's dramatic and you can see it. And the reason I never paid that much attention to it was with the far field, I'd kind of thought of it as, that's just like antennas, and there's not really any power that you could see there. But when you have the source and the antenna, in this case the second coil, in resonance, there actually is a lot of power that transfers. And the behavior, as we'll get to, is much different. So we'll talk about it just for a minute or two, and then most of the video will be me just kind of demonstrating it, because that kind of illustrates it much better. But I'd say that when you think of transformers where you have two coils, they're almost all tightly magnetically coupled. They have, the magnetic coupling close to 1, which is a related concept. When you're in the far field, it's a weak or pretty much next to no magnetic coupling. It's all radiative. So all of the transformers that we see conventionally are all dominated by the near field effects. And that's even with like high voltage flyback transformers that you conventionally see. When I sat down to do this, though, there's one transformer where it looks like, wow, there's actually a big space there between the primary and the secondary. What's up with that? Why would you do that? A Tesla coil. A Tesla coil is not going to be dominated by the near field. It's going to be probably dominated pretty much by the far field. So really, you got your primary there, and the secondary it's like an antenna. So let's just talk about it real quick on Wikipedia for a moment, so this might make a little more sense. I mean, it doesn't make sense to me either, but it was fun looking at it, and you can kind of see what I'm talking about once we put everything on the oscilloscope. So here's the Wikipedia write-up on the near and far field, and let's go through this quickly. The near and far field are regions of the electromagnetic field around an object such as a transmitting antenna. In our case, it will be a coil that's in an LC tank circuit. Near field behaviors dominate close to the transmitter, while far field predominate at greater distances. Far field E and B field strengths decrease following an inverse square law. And here, if we just hover over this, they kind of give us a nice illustration there of why you get this inverse square law, is that it's spreading out as it goes a greater and greater distance from the source. And so it's equal to this surface area that gives you the inverse square law. So one reason I wasn't interested was I thought, well, there's no power transfer. It's all like antennas. But there are a couple things that I should have taken note of. One, we were talking about Harold Wheeler, who gave us the formulas for induction that are still used today. And we also learned he built the largest antenna in the world. So, I should have been thinking, all right, why did he do that? But then also, just in consumer electronics now, you have the ability to charge your cell phone with this far field. You just place the cell phone on a mat, and it's not directly coupled with a wire, and it's probably far enough apart, I'm pretty sure, that it's not really a tight magnetic coupling either. So that's power being transferred, even though it's the far field. Well, I guess I'd also say, they're even talking about charging like Tesla cars that way, electric cars that way. So it still doesn't fully make sense to me how you get the the power transfer. But what I will say is that when you have your source and your antenna, you know, your what are the terminology they use, transmitter and the receiving antenna, or in our case the primary and the secondary coils, when you have those in resonance, then you see that there's actually really pretty decent power transfer, and the behavior is much different than when you are dominated by near field effects. So let's stop talking theory here and just look at it, and that probably explains it a lot better than me just blabbering on here. So here we go. So here's a coil that I threw together, and part of it was just to see how big I could print something on the 3D printer in one piece. So it's 8 inches tall by 8 inches wide. And the first thing to note about it is that it's bifilar. So there are two adjacent strands right next to each other through the whole thing. And I was trying to look at setting it up as a counterwound, and I did set it up as a counterwound. If you want to set it up in a counterwound fashion, the two strands, one there with a piece of tape and then one down here with a piece of tape, that's one strand, and then the non-taped is the other. So you would take the taped strand from the top, connect it to the non-taped strand from the bottom, and you have your counterwound coil. I'm slowly forming ideas about that, but to be honest, I don't know. However, we can do another thing with this, which is fun, and that is we can look at it and demonstrate the behavior of the magnetic near field. So you have these two wires adjacent to each other going up the coil, and so we'll just take one of them and we'll use the tape strand and we'll put it into this circuit where we'll take a 1UF cap. So if you can see that now, we have a 1UF cap there, and this is coming from our power bus lines. And so when these switch on through the two white switches there, those are also opto-isolated solid-state relays, then the cap charges up. Then we put our coil from one end of the cap, in this case the positive, out to this other switch. And so when that switch closes, now this can go to here, and then this can then discharge, going from here around the coil to here, and the cap discharges. And if we let the discharge go for a while, then we have our LC tank circuit, and we get to see it ring. Now, while I don't understand the counterwound thing too much yet, one thing I will say, as a byproduct of having a bifilar, if you're only using one of the strands, then the other strand is a spacer between each layer. So in other words, this has a high Q factor, really high Q factor. We're not really going to, maybe if I get a chance I'll show it. These are 1UFs. You can go smaller and smaller, faster and faster, and I haven't seen it running into much proximity effect or skin effect at all. Just, you know, considering the other wire is not doing anything but being a spacer. So you can really get this thing to ring. And if I get a chance, I'll try and show that. But right now what we're going to do is we'll discharge it and we'll look at it. And then we're going to put another cap on, also a 1UF, on the adjacent wires. And because, as I said, those wires are right on top of each other, the way the magnetic energy will transfer will be dominated pretty much entirely by the near field. And so let's start and take a look at what's going on. So just to start to get the lay of the land before we even start pulsing anything, here we've got it hooked up to our meter, and the direct current or straight line resistance is 19.8 ohms. So a fair amount of resistance, because this is 26 gauge and there's a fair amount of it. But what we're interested in is induction. And it has a fair amount of induction, 7.0 I suppose we should call it 7.1. So if we go to our trusty spreadsheet here, and where's the cursor? And we put in 7.1, and it's not a 0.01 UF cap. Right now it's a 1 UF cap. What do we find out? We find out that that particular combination will resonate at that frequency of about 1.88 kilohertz. And if we wanted to get 12 waves, it would we would leave it connected for 6.35 milliseconds. So that's what we know there. Now we can do one other thing just to have a little fun here. So that's the frequency this thing will be running at, 1.88. If we go back here, 1 and that's close enough. It was 1, so it's right around there, 1.9 kilohertz. And so the Q factor actually kind of stinks here. I'm probably going to go with smaller cap. But we'll just get it running with this, and then we'll probably put in a 0.1 or a 0.01 UF cap. So if we go to our code here, the for loop's not doing anything right now, because as soon as it leaves the for loop, there's, scroll, darn you, there's nothing. But the for loop's there so that if you wanted to like pulse the cap 10 times and then, you know, see where things are at, that you have that ability. So pin 13 goes high and that charges the cap, and that's about as quick as you can go to shut it off. You know, I wish you could do it quicker, but that's about where you're at. And then low, I'm sorry, the 100 is charging the cap up, and then the 105 is where it shuts off. So 105 is about as quick as you can do it without a problem. And then pin 9 goes high, and that's when the cap is discharging through the coil. So we're given a delay of 6 milliseconds, 6.35, and that gives us 12 waves, 6.353. We just looked on our LCR that it's not, I think it said something like a Q factor of 4. So if we fire this bad boy up, what do we see? And we're just running at 10 volts. I mean, there's no need to go crazy. We see that, which is pretty much what the meter, the LCR, was saying we would see, is it's ringing with the low Q factor. And so a convenient way to think about Q factor is the number of wavelengths before the magnitude of the oscillation dampens out to about 4% of its original value. So here we start at 10, there's 1, there's 2, there's 3, there's 4. And that's what we were getting this thing. I think it said a Q factor of like 4.2. So everything's in agreement. And the question now is, do we want to go with the high Q? But let's just demonstrate it with this first, and then I'll just show you that this is a high Q coil if you want it to be. So now what we've done is we've added a second 1 UF cap, and this one is connected to the other bifilar winding. So it's not connected to power, they're only magnetically coupled, and we put the oscilloscope on there. So there's the first one. Now if we put the other channel on, what do we see? That's what we see. That's what's going on in here. That's electromagnetic induction. And this is the near field type. What's kind of, it's kind of fun to think about that, you know, you just put that cap in there and it's got voltage flying all over the place. And because it's the same size as the initial cap, they're almost exactly lined up. However, what happens if you try to get at it? i.e. you try to load it. So here's we'll do a 1K, we'll do 100 ohm, and then we'll just plain short the thing. So when I tap this to that line, there'll be 1K ohm of resistance across this. What's going on? Okay, it's back. Across this cap. So let's see now. Let's see if I can do it. Yeah. Now, the thing to note here is the yellow line. The yellow line is this one. This one has no electrical connection to this one. it's only magnetically coupled. But when we start to load this one, it damps out the other. It loads the other. Let's do a 100 ohm, and then we'll just short it. So now we have it like that, and here's a 100 ohm. So if I connect that, now that's what we see. Our Q factor, our beautiful oscillations, they're nearly all gone. And again, it's kind of interesting. There's no electrical connection between the two. It's all magnetic, but the resistance on here is dramatically affecting the behavior of this one. And so here I've just made it a dead short across the alligator line, and that's what we see. You know, there's no increase in amp draw or anything, but it sure did manage to get rid of all of the induction bouncing around. And if we scale out a little bit here, yeah, see, those are your pulses of the cap charging and discharging, but it's completely damped out now, so you just get that tiny little bit there instead of it just ringing along. And it doesn't matter. I mean, I'll put in a small cap. I just want to look at it again. If you have a Q factor of 100 to start with, you're still going to get this behavior. And this is pretty much what I expect. And this is what you see. The other point I would make is, it's not like just this coil setup. If you have a magnetic flux path, in other words, if you have like a toroid and you have one coil here and you have one coil on the other side of the toroid and there's a good flux path between the two, you're going to see this same thing. It's that they are inductively coupled. There's, I guess, a unit for that, and from 0 to 1, but this has a near coupling of like 1. And that's what you see. That's the near field behavior. That's what you get with conventional transformers, or if you have bifilers where the wire is right on top of each other. But let's just throw in, I want to just throw in a 0.01 to show you that this thing is pretty high Q. So just before we leave this and go to the far field, here's a 0.01 cap, and you can see it's much higher in terms of Q factor. We could probably go faster still. It's only at 18.8 kilohertz, 18.9 kilohertz. This reading's wrong because there's also the time there and then the time there. So one thing I've never done, not with this setup, I've done it with the far field. If we leave this one, which is 1, so 100 times bigger, and we connect it and we don't load it, I still think it's going to dampen it because it'll be trying to send it to the same voltage. This one going to 10 to negative 9.5, and if the cap is matched, it can do that. But if it goes from 10 to 0.95, is that going to be viewed as a drag? Yeah, it damped it out all right. I mean, even zoomed in, you can't really see much of anything. So that's what I expected, but even more dramatic than I expected. And that just shows you the importance of having the two caps be the same size and hence resonating at the same frequency. Much different behavior. Let's go to the far field now, the goofy one. So to look at I don't know what it's called. I'll call it like radiative coupling. I actually made 3 of these and went from the 26 to the 22 gauge wire, so they didn't take too long to wind and whatnot, and they fit on the desktop better. So we'll take a second one and we'll put it up flush against here. Now you say, well, one wire is right next to the other, but the majority of the field is, if you look at it from, say, the blotch wall to the blotch wall, there's a good space of a few inches at least, even if it's right up flush. There's different behavior depending on where you're putting it as well. But let's first get the lay of the land with this coil. Okay, our resistance has gone from 18 to, or whatever it was, down to about 2.3, and our induction, that's not it.
Our induction is 1.23, 1.24. I'll call it 1.24. So let's go back to a 1UF cap, 1.24, our trusty spreadsheet. We see that it'll be 4.52 kilohertz. So if we go and set this to 4.52 with the 1UF cap, instead of the Q being 4, the Q is 14. So less wire, better Q. Importance of the wire diameter. Although because it's not bifilar, I mean, you will run into some skin effect before getting out to, say, 100K or something like that. But this is good. So let's put a 1UF on here and confirm that it has a bit higher Q factor than the 1UF on that big coil. So here's our 1UF cap through here at 10 volts. And just like the LCR meter said, this is actually a better Q factor than the 1UF on the bigger coil. So that's nice. And now what we're going to do, and this is where it gets kind of cool if you ask me. We're going to take a second one of these with the same number of lines, same gauge of wire, hooked up to the same cap. And we saw what happened with that scenario with the bifilar. So what happens now with this? And you know, there's nothing real precise here that I'm doing. I just got the two coils here. And let's leave them a good bit apart here, just to start. And we've got our same size cap. We got the other channel of the oscilloscope hooked up. So what happens? Now that's what we see. And let me try and zoom in. Anyway. Yeah. There's a lot to talk about. So if we just sort of freeze it and zoom in here, this isn't the same as the other one. And it's a complicated behavior. It's sort of generally 90 degrees offset, but they're not staying matched up. Now, it might be that this is really sensitive to, this is like a 1 and that's a 1.03. I'm not to the bottom of this by any means. But you would kind of think, and I think they sort of do, they do eventually like to just kind of go on a more stable pattern, 90 degrees offset, but you can see that this is different. Now, let's make it live again. Zoom in a little bit. Wrong place. Oh, we'll zoom out. Now, if I bring this in, then it starts to get even stranger. That's what it does there. So that's odd. And then it does it on the other side too. So we know a couple things now. We know that this coil is influencing the behavior of the oscillations of that coil, even when it's not loaded. Whereas when they were tightly coupled, the two just lined up perfectly in sync. And here you're getting this sort of complicated pattern going on, and it depends on the spacing there. But that's not the strangest to me part. Okay. So we don't need stinking resistors. I'm just going to put a dead short across this secondary right now. That's what we see. That's pretty interesting, isn't it? I'm going to unshort it. Wait a minute. Unshort it. Short it. When it's shorted, like you'd be drawing off power, this oscillation's unaffected. Now let's bring it in close. Now, this is affecting, this is unloaded, this is affecting, that damped that out, but then it increased that one, and then it did a goofy thing there, and then this one does a goofy thing a little bit later. But let's short it in close. Same thing. Goes right back to as though there's nothing there. So what's that telling us? That there's not a magnetic linkage. I'm using my own terms. I don't know if this is what they use for the people that actually know. There's a radiative or antenna linkage. And so this shoots out to here, and then this rebroadcasts back to there. But they're not magnetically linked, because otherwise when I shorted that out, it would have shorted this one out too. It would have damped this one out. But it doesn't. When it's shorted out, this just goes back to normal. Okay, so we can see how this is behaving. And see, it doesn't start off that big, but because they're the same caps, they start to interact. And so this oscillation actually increased here, although this one damped out. Now let's spin it around. Now it does this. Recall that one was going down and then that one was up. Now this one is up, this one's down. It damped this out, but it got added to there. Now the third one's lower instead of the third one being higher there. And you still have this there, and then that there. And that's something I'm really trying to figure out, is what's that all about. And it's either that these things have to be perfectly matched, and the 1 or 2% that I have with different caps, and the induction is probably 1% or 2 different, is making that difference, or it's something else that I don't understand. So I'm also, you can see now why I've got another switch there, is it's seeing can you do anything with that. So I don't know, but again, if we short it out with it turned around the other way, right back to normal. So just to kind of come out with it, there's a couple things. So I mean, the first thing is, because we know that you can load this without affecting this oscillation, it would be nice if you could line these up so they weren't 90 degrees out of phase. And I don't know if that can be done. And I don't know what that is. That's another thing I have to figure out. But if they lined up, see, the problem you have right now, let me get a pencil. If you shut it off here, you'd say, hey, I've gotten more than half my initial voltage back. You got 0 in the other cap. And then you say, oh, well, there's a lot in the other cap. Now your initial cap's at 0. So you can't get at anything right now. If they lined up like we saw with the other, where they're just tracing over each other, then this would be coming back, and this would be high. Or if they were 180 degrees out of phase, you could do the same thing. But they're 90 degrees off. So I don't know what I'm doing. That's what it boils down to. But it's man, it's fun. What's the last thing here? Oh yeah, we'll do a small cap into a big one. We haven't done big into small, but I'm not going to worry about that. We'll do the small into the big, and then I'll throw a little bit of philosophy at you on this. So recall with the other setup, when we had this 1 UF and a 0.01, it was viewing it as like a dead short again, and it damped the heck out of it. It damped it to nothing. So I never even disconnected this. I put in the 0.01, and it's oscillating right away. Now what I want to see, what you should be able to see, I always go the wrong way there. Oh, it's too big. If it was like, yeah, everything's hooked up. If it was only 10 times bigger, you would see this other cap oscillating at the similar kind of frequency, but a smaller amplitude. So again, a much different behavior than before. So I find the most interesting thing here is that the behavior under load is entirely different in terms of the LC tank oscillations. And these oscillations, since if it's loaded, it's not doing anything to that, then they're going out here, and then they're going out here, and then they're going out here. They're also going out the other side. And while there's some directionality to this, they're going out the sides too, and it's just forming a bigger and bigger sphere. And so the radiative effects, as we saw when this was further out, the amplitude was lower of the oscillations. So it's following an inverse square law because it's the surface area of the sphere expanding as you get away. But it's going out, and you could have another one, here, and you could have one out there. And when you load them, it wouldn't be doing anything to this this oscillation. Now, again, I don't really know what I'm doing, and it's easy to say, oh, that's weird. It's a lot harder to, have something where it's just not like, well, I'm just going to buy a solar panel from Harbor Freight. that's usually a good bet. Like, buy a little $50 solar panel and you're all set. But you can think of something really weird with this. And I'm probably dating myself a little bit, but sound waves, there's a lot of overlap with the electromagnetic waves. And so there used to be an ad for Memorex tapes, and they'd have a woman sing, and she would sing at the resonant frequency of a wine glass, which I guess maybe you just kind of rub your thumb on it to get what the note is. And she'd do that, and it'd start shaking, and then and the wine glass would shatter. And then they would, hit the tape and do the same thing. And is it live or is it Memorex? And it was a very clever ad. So seeing as we just saw here is that loading it doesn't change this. What if you had two glasses right next to each other? What would happen? I think the two would shatter. Now, there's probably some directionality to the singing, but you could probably get maybe 30 degrees, and I think the wine glass was probably like 5 feet away. So now you can line up 20 or 30 of them. And you can probably go 30 degrees up and down. So I don't know how many you could fit, but 30, let's say maybe like 300. Now maybe, let's say that 5 feet was right at the limit. But you come in some. So what I'm getting at is, for her singing the same note, they might have been able to set it up with like 2,000 wine glasses, just all there, and the same note would shatter all 2,000 of them instead of just the one. I think that follows from noting that the oscillation doesn't become damped when this thing is shorted out. But again, it's just one of those sort of goofy things to think about. I don't know really what it means, and I don't know how to do something useful with it, but just thought I'd kind of end with that, because I don't see how that doesn't follow, and I suspect that is the case. But I don't know any opera singers or anything like that, and so we'll skip that experiment. Okay, I hope everyone had fun, and got to get the parts for going back to the spinning pulse motors, and and other motors too. So take care, stay healthy. Talk to you later. Bye.